Okay. Okay, so I will start with the presentation. Today we will focus on the flash calcination of clay. First of all, a short introduction of FIB for who doesn't know very much our company. So we are an industrial engineering group, rich of more than 200 years of history, and we serve the great industry all around the world, with a strong focus on R&D, with a lot of patent still in force. We are strongly committed to reduce CO2 emission within the group, and as a FIB in the cement industry, we offer various solutions that can help our industry to significantly reduce the CO2 intensity of the cement, and for instance, with innovative and a solution for concrete recycling, or the most efficient mill, also with the raw mill, and of course, as it has been discussed today, with switching to reduce the clinker ratio in the cement with clay calcination. So FCB was a kind of pioneer in the flash calcination process, with industrial realization back in the 80s and 90s in mineral industry, such like alumina. But with the coming of clay calcination, we have, let's say, to rethink and reinvent our design because of the specificity of this material. As you know, clay is a material of great diversity, with very different, from one side to another, very different mineralogy and chemical compositions. In addition, there is now a trend for circular economy in order to reuse waste material in, for instance, in big construction work, and this gives a very large panel of materials, and which has an impact, a direct impact on the way we should activate them. Shortly, when to make the calcination, as has been explained, you produce this highly reactive material, metakaolin, which is very reactive, and in case of overheating, will react with other minerals to form new compound. It's sintering phenomena that you have when you fire clay to make bricks, for instance, and this leads to a loss of reactivity. And in addition, this phenomena, as you see on the picture, can cause clogging in the industrial equipment. This picture from tests that we made on, let's say, old style calciner with clay that quickly clogs the equipment. This is why we redesigned completely the calcination process specifically for the clay. The main thing is that we have done is to really dissociate the different process steps. So, and we will see later the interest of the first one with the drying and grinding to high fineness and with narrow size distribution in order to have the best results in calcination. After grinding, so the material is sent to the preheating step with cyclone, much like in a preheater tower of a cement plant, and then undergoes the the calcination. Once again, the heat generation is here separate from the calcination. This has several advantages. First, it avoids overheating of the fine clay particles because we control accurately the hot gas flow temperature, and we have no direct contact with the flame. In addition, it allows to use a large range of fuel, including alternative fuel and biomass. We'll see also later. This is because the temperature of calcination is somehow lower than in a cement plant calciner. So alternative solid fuel will not have a complete burning in such environment. So the separate combustion allows and get rid of this problem. Next step, as it was discussed also before, there's usually a need of color control and to get rid of the beautiful reddish color of terracotta products, but which is not very well accepted so far by the market for cement. So we do have here also a dedicated loop with introducing of reducing gas, which allows transformation of hematite to magnetite and get the gray color. Final cooling can be done with air, then without reoxidation when the temperature is low enough, and this hot air can be used as a heat recovery for the combustion. Finally, so the end product can be sent to the cement grinding or store for other application in concrete, for instance. So now, in order to develop this technology and help our customer to really assess the potential of their material, we have built a new pilot plant in our facility in north of France, and develop also all the comprehensive method to analyze the material and test it. So it ranges from the laboratory test and up to the calcination in the pilot plant, in which we can produce few hundreds or a few tons of products that we can send back to our customer to make his own test, his own recipe, and so on. Also, of course, including in the pilot the color control and the color measurement in our lab to assess the color of the product after reduction. Now, I would like to focus on the calcination parameters that we have studied. Calcination parameter, calcination process is governed by three main parameters, which will be the particle size, the temperature, and the residence time. Here's this example of study we made on a clay. Tested with three different granulometry, from very coarse to fines, different temperature and different residence time. Sorry. On the vertical axis, so you have the reactivity measured by the Chappell test, and we see clearly the effect of the main effect of the parameters, and with the clear effect of the granulometry on the reactivity. The other parameter being much less significant. This is shown also on the distribution function of the various tests. we see the very big difference between the different granulometry. So here the reactivity is on the x-axis, and so you can see clearly the low reactivity of the coarse material, which cannot be fully compensated even if you increase the temperature or the residence time. And this is clearly because to have the highest reactivity, well, it was discussed also in the previous presentation this morning, you need the complete dehydroxylation of the clay, but without overheating. And on a large particle, whether you are a little bit too low in temperature, then you have under calcination, let's say, in the core of the particle. If you go higher, you will start sintering of the shell of the particle. To look a little bit more in detail, so the grinding is an important phase because of what we have seen before. We need very fine distribution of the particles, and it gives also the possibility, this fine grinding, to evacuate the coarse quartz particles that may very often be also mixed with clay minerals. And so by doing this, we can enrich the feedstock in clay mineral, which can be activated. The choice of technology will depend mostly on the clay type, the clay humidity, and rheology. And we compare here with hammer mill, which will, on the opposite, have a much wider particle size distribution and will not be so accurate after for the calcination. Okay, excellent. Okay, so next important thing is the heat generation. So as we have said, we have separated it, so we are able to burn different kind of fuel. Once again, the technology will be adapted according to the typology of fuel. From fluffy material, we can use suspended combustion, like a little bit like in a calciner, and for coarse particle, use a great incinerator. And this allows to have a very high substitution rate, so to reduce again the CO2 intensity of the final product. And even electricity could be used, as actually the heat is generated separately. There is no contact of heating elements with the particles. I finish the layout also. There are strong demand to have a compact and low height, so this is something also we have worked, and we can reach less than 50 meters for 800 tons per day capacity. And so this is my conclusion. So we really focus on the process to have, let's say, the maximum of flexibility in terms of materials that can be activated to get the greatest activity, and then a great substitution, and with any kind of fuel, which is also a great help for ROI and cost, operation cost.
Thank you.
Sorry. Yeah, you're welcome.